Let's talk about direction cosines for three-dimensional vector. Before that, let's talk about a two-dimensional vector. And we'll see why one angle is enough to understand the direction of this. We already know that there are two parameters in a vector, that is the magnitude and the direction. Now, how do you get the direction of this? This topic is more about direction, so let's go ahead with this guy. Now, I know that the coordinates of the point A are nothing but 3, 3 in this special case, and I know that that's x-axis and that's y-axis. Now, to understand two things, that is a magnitude and the direction. For magnitude, it's pretty easy. I know that this is 3 and this is 3, that's 90 degree here. So I can just use the square root of 3 squared plus 3 squared. That goes like root of 18, which gives me the length of this guy, that is root of 18. We got this thing. Beautiful. Now, how will I get that angle is the question. To get this, we use trigonometry, and we know that I understand that's the opposite and that's the adjacent if this is theta and if that is hypotenuse, right? So it's very simple, guys. And I know that the opposite and the adjacent are nothing but the coordinates of the point A in this case. Now, is there a connection between these guys and theta? Of course, there is one. What is it? Tan of theta. Tan theta gives me what? Opposite by adjacent. And we know that one angle is enough for me to define the direction of this vector completely. All right. So if I say that you need to, in this case, I can say that there's 3 over 3, which is 1. And in this case, if tan theta is 1, then theta has to be 45. So if I tell you to take a vector or to draw a vector which is 45 degrees with the x-axis and whose magnitude is root 18, it's pretty easy. You can do that, right? So just draw the x and the y-axis, take an angle of 45 degrees, and draw a length of root 18, and you get the point A. Now, is this as simple as this in a three-dimensional vector? Not exactly. In that case, one angle is not enough. Right? Second thing to note here is these are the two coordinates, and I'm connecting the coordinates with the angle directly. I didn't even have to find the modulus of the vector to get the angle. All right? So I know that the angle is nothing but tan of inverse of y by x, where y and x are nothing but the x component and the y component, basically. All right, we got this, guys. Let's go ahead with three-dimensional vectors and understand what is this. So let's talk about the three-dimensional vector now, and we know that this vector needs at least 3 angles which it makes by x and the y and the z-axis to define its direction completely. All right, look at this. Let's visualize this. This is the vector I'm talking about, but OA in this case, I can see it makes 3 angles, alpha, beta, and gamma with the x, y, and the z-axis. Look at that. And I can see if at all I move the point A, all the 3 angles will change. It means we need 3 angles to define its direction incomplete. Look at that. If I move this point in any direction, basically, I can see that alpha, beta, gamma, all the 3 angles are changing, basically. Alright, guys, let's see why and how we should find the direction cosines of this vector OA. Now, beautiful, guys. Why not direction tangents and why not direction sines? That's also important. Now, look at this. Given to me is that's a vector, okay, and it's got a point that is A with coordinates 3, 3, 2. I can say that is the x component, or I can write x1, y1, and z1. These are the components of the vector OA. And we also know that we can find the length of this guy by the simple formula, which is root of x squared plus y squared plus z squared. So overall, what is given to me in a vector is this point. And if I know this point, I can find the length. So overall, this point and this length is what you have. With the help of this, can I find the angle is the question. Now, I know that this part is nothing but the x component of the vector. It means it is this component is what it's talking about. It means if I know this is 3, 3, 3, it means its x component is 3. Okay. And if I know these 3 points, I can also find the length of this guy. I can very clearly see that this is alpha, which I'm looking for, and that is the hypotenuse. And if I draw a perpendicular here joining these 2 points, I can see that perpendicular I drew from the point A on the x-axis, and that makes a right angle triangle here. I'll show you that to you. Look at that. If I move this guy, I can see this plane is basically joining the point and a perpendicular on the x-axis, which contains the angle alpha, right? And if I see it in this direction, I can see that is a hypotenuse. This is nothing but 90 degrees here. That is a hypotenuse, and this is the angle alpha, and this length is nothing but the adjacent. Now, what connects the adjacent and the hypotenuse and the alpha? It is nothing but cos. So we can find cos of alpha, which is adjacent, which is also given by its x component, because I know the coordinates of the point A. It's easy to find this guy, that is 3. And how can I find the hypotenuse? We already know that is given by x squared plus y squared plus z squared. So that's why we take the direction cosines. If I had to find the a tangent, and I should know this length and this length both. I don't have any idea of this length. So it is our most easiest and the most comfortable way to find the direction cosines. Whatever it is cosines, or in this case we had the tangent basically, but it does give me the direction. So that's why we use direction cosines only to find the direction of a three-dimensional vector. Well guys, now see what is angle beta and how do you find the cosine of the angle beta. Look at that. That vector A is making an angle of beta with the y-axis now. Alright, so how do you find the direction in this case? So we have to do one thing. We need to draw a perpendicular from the point A and the y-axis. So let's do that. So that is what I'm talking about. Okay, that angle is basically a 90-degree angle here, and I can see that this guy is the hypotenuse here, which can be got by the same formula, x squared plus y squared plus z squared. Okay, and that is the angle beta for me. Alright, and this is nothing but the y component of the vector. It means this guy is what I'm talking about. Okay, so I know this guy, and I know this length also by the coordinates of the point, and I know the angle beta is here. Can I connect these three guys? Of course. Cos of beta is given by adjacent, in this case that is nothing but 3 divided by the root of this length is given by the root of x squared plus y squared plus z squared. I can write x squared plus y squared plus z squared. So we got cos of beta also. Let's see how to find the cos of gamma, or the angle made by the vector and the z-axis. I can see that is the vector and that is the z-axis, and I can see that is the angle made by the vector and the z-axis. That is gamma for me. Now if I draw a perpendicular from here, I can see that is a right angle triangle again. And in this case, I can very easily say that, yeah, we have this guy, which is nothing but the angle gamma. Yes, and this is the hypotenuse again. I can say that's the hypotenuse, and this angle here is 90 degrees. According to this, I need a connection between this side and this angle. And that exactly is nothing but adjacent. That is adjacent, that's hypotenuse, and that's gamma. So can I write cos of gamma is nothing but this length, and this length is nothing but the z component of the point basically. I already know that the point is given to me. If this is given to me, I can find this guy very easily, which is nothing but this thing. So that is 2 divided by the root of, I can say this length is always given by x squared plus y squared plus z squared. So I can actually get all the three angles and y cosines only, because there is a connection between the angle and this adjacent basically, and adjacent is nothing but this guy, and hypotenuse is always got by this thing. So that's why we use the direction cosines, guys. Beautiful.